To continue from the last class, so you are given a couple of conditions. First, I explained two tables already. You are told that given the draft and the half areas, first table. The second table gives you the stations and half ordinates. So two tables we have already defined, and other than that, you are given another table, that is, I mean, you will be just given this table, you will be asked to fill the rest of it, like half area, you are already given the half area, means, so you can fill from the half area for different drafts, you can fill it here, like that. Means you take this table, you take these distances, 800, 1600, it comes here. Now, this is something I actually, after do this, we will spend a little more time. The Simpsons multiplier is actually a little bit confusing when you have stations like this, 0.25, 0.75, then it becomes 1.25, then it becomes 2.25. Actually, this I should write 3.25, 4.25. Now, if you have 1, 2, 3, 0, 1, 2, 3, 4, 5, there is no doubt, there is no confusion. It's 1424, right? 1424. I have to check it. I think it's 1424. That thing you have to write. But we'll do this later. This becomes a little different when you do different kinds of stations. Means 0.25, 0.75. You have other terms coming. We'll do that. One simple thing you could do is you know how to derive this, right? Can you derive this quickly if you want to? What should be the Simpsons multiplier? Means you know how to derive that Simpsons that formula, that derivation you have to remember. Means you have to know how to draw that like this. You'll have a curve like this, and you divide it into, and like y1, y2, y0. These are y0. These are x0, x1, x2, and these will be y0, y1, y2. Now, just do the best way is you take that Simpsons that formula, you divide it into some 6 stations, the 6 points, y0, I mean x0, x1, x2, x3, x4, x5. Then find the area of, means you take the total area under that section, you derive the area under that section, assuming that this distance is, you call, means let us suppose you assume the distance between 1 and 2 to be h. Let's say that is h. So 0.25 and 0.75, the distance is 0.5 h, right? The distance between station 1 and 2, or between 0 and 1, if it is h, the distance between 0.25 and 0.75 is 0.5 h. So like that. So you take this to be 0.5 h, 0.5 h. Next one is 1 h. That difference is coming because of the different type of stations. With that, you derive that, rederive that equation for the area. Actually, I will ask you to do that for some time, and when you do that, you can get the real value of the Simpsons multiplier for that particular case. So maybe if you are having a, to be honest, I think a problem like this, if I give for the exam, this will take at least 45 minutes to do, maybe at least 35-40 minutes to do, I think. But one thing about doing a problem like this is, if you are able to completely do one problem like this, it shows that you have kind of mastered Simpsons multiplier rule, and also these things as half areas, what is volume, what is moment, and I by del, all those things. So you might end up with such a one big problem. Okay, so and so that is, so in this case right now I am not deriving it, but we will derive some special case of Simpsons rule after this. So let's suppose that the Simpsons multiplier in this case, it really comes like this actually: half, 2, 3 by 2, 4, 2, 4, 1. Okay, it will end up like this for this particular. We will derive it and see how it comes. And now you are also told that So now there is something here after this volume which we call as lever. Lever means when you multiply the volume with some distance, you will get a moment. That distance is called as lever. For example, if you have a ship like this, and volumes in this case we are actually finding like this, so not stations. Let's say that you have water lines. Now suppose you are finding the volume of this region, you multiply it with this distance, okay, you will get one moment. Then you take this whole volume, or rather maybe this volume alone, this region alone, then you multiply it with this distance, you will get another moment. So those distances are called as levers. That's what we have mentioned here as lever. That is the meaning of that lever. This is the volume, and then so 1000. So this is actually giving you the Simpsons multiplier, or rather this is 1, 2, 3, 4, 5 and 6. This is the first moment. Then you have so this volume is actually your 2 into 3. Okay. Now that won't give you really the volume. You have to multiply what with what to get the volume really. This distance means the distance between each station. Here you are multiplying, when you are multiplying with Simpsons multiplier, you are actually multiplying this a kind of that fraction 0.25 to 0.75 will give you 0.5, that is a fraction. You have to multiply it with h. When you multiply it with h, you will get the volume, but this will give you a function of volume. I won't write it as volume then. This is a function of volume. So this way, this is given here by 2 into 3. Okay, this is the half area. So you are multiplying the half area with the length, with that fraction. When multiplied with length, it gives you the volume. So this is the half. So this becomes 800 into half. This will become 400. 1600 into 2, 3200, like that. Okay. So this is this into this. This is this into this. So this gives you this value. So for the exam or for any assignment or anything, I am not going to give you what is the definition. So you just have to know half area is this distance. It is a half area. It's not that distance. That half area is that sectional area. Area into this distance will give you the volume inside. It's not the distance. Sorry, I told it's not the distance. What I mean is at each y, what is the sectional area? So you are getting that area into that distance. This horizontal distance will give you the volume in that area, or in that volume in that region. Okay. So that is the way to calculate the volume. So looking at this, even if this table is not given, you should be able to generate this table. That's what I am coming to. Probably you are just given these two tables, which will give you the half areas of water plane and half ordinates of water plane. Whatever you are given, you should be able to find the volume. Then you need and how do you find the function of? So these levers will be like this. First one is at 0. Okay. These are different drafts, not different stations. So 0, 0.5 I keep saying station. 0.5 is this lever. So okay, in case I have confused, it's not station. I myself thought of it as it's not station. It's the water line. Okay, that is, it's like this. It's not like this. It's not areas like this. It's like this. Yeah, I told you wrongly. Sorry. That is, we are talking about volumes like this. Means you have, it's like this. That is, you have the area multiplied by this length is giving you the volume. That is the volume, not this distance. Sorry. So so this lever is actually this distances from the bottom. So when that volume is multiplied by that lever, you get the moment. That's called the first moment of that volume. So 3000. So in this case, 400 into 0 will give you the first moment, 0. 3200 into 0.5 will give you 1600, the first moment. Now, what is the point of finding this first moment of volume? Think of that and tell me what will give you. What is it to find? I mean, to find what are we doing it? Kb. That's what. The idea of this first moment is to find Kb, which is given by Kb is equal to the first moment of volume, the sum, the total first moment of volume divided by the total volume. Means you calculate each of these, you find the sum, the total, divided by the total volume here. Of course, this has to be multiplied with an h to get the total volume. Once you have that, the sigma first moment of volume divided by the total volume will give you the Kb for that whole volume, means for the whole ship, in fact, for that particular draft of 5.25 meter. Now, just one thing to note here is, in this table, in the first table as well, see, you are starting here with a draft of 0.25 meter, right? You are not starting from a draft of 0, means you are not starting from the keel, you are starting from some 0.25. This is the first waterline that is given. So, all your calculations, if you whatever you do using this table, that Kb, what you get will be the Kb of, I will draw this figure. So, this is waterline 0.25. You will get the Kb from this Kb you will get, or Kb of, let us say that this is 5.25, this is given as a draft. So, you will get Kb of this volume, you will not get anything about this. That is why they have said that below 0.25 there is an appendage volume of 150 meter cube. They have said that this volume is 150 meter cube, and that volume has a Kb, let us call it small kb, Kb equal to 0.2 meter. The Kb of this volume, this distance, this Kb is 0.2 meter. Okay. So, the problem is not very simple, once you understand the different points of it, of course, it is simple. So, these are the things. So, first you have to find, you will have first from the table you will get this whole volume, this shaded region that I have shaded here, you will get this volume, you will get the Kb of this shaded region also. So, this you will get the volume and Kb of this shaded region, and by using the additional data given in the problem, you can find, you know, the Kb of this, then you have to find Kb1 V1 plus Kb2 V2 divided by V1 plus V2 will give you the Kb of this whole ship. That is the first term, and next is to calculate the I, that we will come to that. That is, first let us do this, that is, therefore, volume is this, we are using this function of volume. From this function of volume you get the, first of all you have these functions of volume different, let us call this sum up and let us call this sigma function of volume. Okay. Means all this is added up, that is the meaning of this sigma function of volume. So, the total volume really is 2, because it is half ordinate. So, you need this 2, that will give you the total volume, 2 into, this is the formula, you know how this h by 3 has come, it is because of that definition of Simpson's rule, it is h by 3 into 1424 in general for a body, for a shape. Then, so this becomes, alright, you just do that, that is okay. So, this is how you find the volume of that whole section. So, you get this volume that we have seen. Okay. Then, now we have to find these are small things, but you have to note this, that is, note that we have put the keel point as 0. So, I will just explain this. Let us say that this is the Kb that you are getting for this whole thing, Kb minus 0.25 will be equal to h into sigma function of first moment divided by sigma function of volume. The right side is obvious. Let's say that we are finding the Kb here. The Kb is equal to h into this. I think is obvious, no? H into function of first moment. Function of first moment. This thing sigma function of first moment. This one, okay. Sigma function of moment is the sum total of all these moments. So sigma function of first moment into h divided by sigma function of volume. Isn't there an h by 3? Usually I think there should be an h by 3. I will check this and tell you, but I believe there should be a 1 by 3 h. 1 by 3 h into sigma function of first volume, first moment divided by, this is function of volume, that is this. This is the function of volume, okay. That is all this volumes added up. So actually I am telling a lot of things. If you are not really following, then you are going, the whole thing will be confused. So is it becoming clear to you what we are doing really? Because I have said a lot of things here and there, sigma volume, sigma function of volume. So if the whole thing becomes a muddle, then the exam is going to be a disaster. So should I explain once more? Yeah, I'll do that. I thought it'll, because I've said a lot of things. So that's why this problem is, before I explain this problem, let's explain the basics first of such a problem. That is, means details I'm going to skip, like 0.25 and all, let that go for the timing. Let's explain what the important things are. First of all, the problem given is this, that is, you have a ship, okay, and you are given the table that, you are given a table which says that at different drafts like this, first of all, it's not that the ship is put and it is at a particular draft. It means that at different drafts, if the ship is at different drafts, what is the value of the half area of water plane? Means this area is given, okay, this area at one draft, area at another draft, area at another draft, like that at different drafts it's given. So that is the first data that is given. So while making this table, this is the first, so I'll make the table again in a systematic fashion. So same table I am writing in a different fashion. That is, you have the draft. So that is point, I'll write the value also 0.25, 0.75, 1.25, 4.25 and 5.25. Okay. So these are different drafts, and at each of these different drafts you are given the half area. So we'll write the half area. This is a given data. So it says 800, 1600, 2300. So it's clear to you what this area is, right? This is the half areas of the water plane at different drafts. Now we need to find, given that half area, what is the volume below that? We need to find that volume enclosed in that region, means from the keel to that height, to that draft, what will be the volume enclosed? We need to find that. How will you find the volume? Volume is always that area. It is the summation of areas, area in summation of volumes, first area into the length for which that area exists, right? So that is till the draft below, means it's like this, different drafts. So here let's say the half area is 1, okay. Now I want to multiply it with this distance. This draft is, let's say 3.25 and this is 2.25. So till 1 into that 3.25 will give you the means you need to, not 3.25, 2.25 to 3.25, this region, this volume will be given by actually this area into this distance, right, multiplied by a Simpsons multiplier, that is always there. So that will give you this volume. This volume is given by this area, the area here, multiplied by this distance, multiplied by the Simpsons multiplier. That will give you this volume, and summation of all these volumes will give you the total volume beneath the whatever is the final draft. So this is what we are doing here. So this is what I mean. Simpsons multiplier has to be there. That don't forget. That is Simpsons multiplier. Now the exact values of that I'll explain next. But let's just assume that the Simpsons multipliers are like this for this problem. Like this 4. So you will have Simpsons multiplier like this. Now the volumes that we are finding is this, like this. This is, let's call this, this is V1, V2, V3. So the volumes are clear. What volume you are calculating and how it is coming because of this multiplication. So this multiplied gives you, so what are you having? Let's call this 2, this is 3. So 2 into 3 is giving you a volume. Okay. So the volume is 800 into half, this will be 400. This 400 is this volume, the first volume, this one. This volume is 400. It's not 400, it's actually has to be multiplied by an h by 3, but it's the function of volume. Okay, that is, how are you getting the, means if how are you getting the volume? Volume is equal to, what is the total volume? Volume is, it's defined like this, h by 3 into V1 plus V2 plus V3 plus V4 plus V5, like that. This is not volume, it is a function of volume. It cannot be a volume because there is an h here, right? So it's a function of volume. So V1, V2, V3, V1, V2, V3 are given by this into this. Okay, because this into this into, so V, this small V1 into h by 3 into that Simpsons multiplier will give you the volume of that section, this V1. So like that you will get V1, V2, V3. So this is giving you some function of volume. When multiplied with h by 3, when you sum them up and you multiply it with h by 3, you will get the total volume under that whole draft. So this is the function of volume. Now the next one is to calculate a lever. This is to calculate KB, means our final aim in doing this lever is to calculate KB. So to calculate KB, note that KB you have to find as the total moment of each of the volumes. I'll write it, sigma moment of all volumes divided by sigma volume. This will give you the KB. Means you find one volume, you find the position of that volume, you multiply it with, so you multiply the two, position of the volume into the volume at that point, you sum each of them up like that, divided by the total volume, that will give you the position of KB, that center of buoyancy. Okay, so that is the purpose. So lever is to find the position of each of those volumes. The best thing is to find the center. Instead of taking the one end, I told you end last time, not the end, better to take the center. So the first one, 0.25, let's see what they have. Basically this problem they have done like this. This table starts from 0.25, means we are finding the volume from 0.25 up, not below 0.25. So let's take this to be 0. The first one is 0. Okay, the next one is, so this is multiplied 600 into 2, so this becomes 3200, and it is between 0.25 and 0.75. Let's take the middle, that is the position of that volume, which is 0.5. Okay, let's take it like that. So 0.5. The next one will be like that. You like between 0.75 and 1.25, that is 1. Is there a confusion here? Is it okay? Okay, and this will be 2300 into 3 by 2. Whatever it becomes, 3450. So this will give you the lever, and this is the function of moment. So function of moment is the product of these two. volume into lever, 400 into 0, 0, 3200 into 0.5, 1600, 3000 into 1, 3450. Okay, this is pretty much how you fill up the table. If you can really fill up this table without any error, then you have more or less got the answer. Okay, next is just, yeah.
Since the 0.25 level is taken to be 0,
yes,
then 0.7 between 0.75 and 0.25, the centroid of this volume will be 0.5 by 2.
If 0.25 is taken as a 0,
then the next level is 0.75.
okay.
So between this is the volume, and the difference will be 0.5 minus 0.25, that means 0.5.
Actually, that seems to be correct, what you are saying. Let me check this up, okay? I have to do this. Yeah, you're right. Wait, no, that's what I am saying is point. Okay, yeah, 0.25 to 0.75 is 0.5 and a half. Let me see that. Okay, all right, then I'll check that and tell you. So, so you do that, then you will get okay. So therefore, the volume is equal to 2 into h by 3 into sigma function of volume so 2 into 1 by 3 into whatever. So that will give you the total volume. Okay, that is the first thing. You find the volume, then you know how to find the volume. Volume is equal to h by 3 into the summation of this volume. So this sigma volume. So sigma volume into, that is the sigma function of volume into h by 3 into 2. That will give you the total volume. Now B minus 0.25. Actually, they have taken 0.25 to be the origin. So B is equal to 0.25 plus whatever they have taken it as such. That's a point actually. I will check that. B minus 0.25 is equal to, actually this should be 1 by 3 h into sigma function of first moment divided by sigma function of volume. So what you are getting here, see, you are getting some B here. Now to get the real B of that, okay, let me look at that figure here. See this figure. So you will get, what you are doing is you have taken 0.25 to be the origin. So this is 0.25. You have taken this to be the origin and you are finding the kb of this. So when you get that kb, you have to add 0.25 to it to get its coordinates in the final coordinate system we are using. That is, our final coordinate system says this is the origin. Okay, always k is the origin. That's how we are defining it. So plus 0.25 will give you the kb for this volume alone. Remember, it's for this volume alone. It's not the kb of, it doesn't include the kb of this region. It's just the kb of this region based on the general coordinate system. So B will be 0.25 plus, that's why this expression comes, B is equal to 0.25 plus h by 3 into this thing, sigma function of first moment divided by sigma function of volume. Now this you will get the value of you will get some value for kb. This gives you the value of kb for this volume above 0.25 based on this as 0, 0, 0. Okay. So that gives you 1 kb. Then now you have to find the kb for the whole. That means that volume plus the volume below 0.25 meter. That is very easy. You have the kb for that, you know the volume of that. You have the kb for this, you have the volume of this. So just same thing. That is, you do like, you can do like this: volume, kb's, moment. So this gives you the total volume of the ship. From the table we have calculated a total volume. This is what it comes to. Then this is that kb you are getting, and this is the moment. This is like, this is 1, this is 2, 3 is equal to 1 into 2. So you will get the product of these two here. Then here you are told, given that this volume that is below is about 150 meter cube, and that volume has a kb equal to 0.2 meter. So you find the product of this again, it comes here. Sum up, you get this volume, sigma volume, you get sigma moment. Then you are getting the total kb of the whole system is given by sigma moment divided by sigma volume again. So this gives you the kb for the, so it's really very important that you, lot of these things like there are a lot of points in here, like finding the origin, shifting the origin, then finding the kb of that volume, 2 volumes, finding the average. So you are going to have a problem like this. So you have to, I very strongly suggest you please do this problem very carefully. Okay, go through the whole details of that problem. So once if this is clear, I think you can. But like what he asked, I mean, that shows that he has understood more or less. So that's a good point. Then so you will get kb, that gives you the kb of the system. Then now how do you find the moment of inertia? Now we need to find bm. This is another problem only. So it's also you have, it's a lengthy process. bm is equal to I by del. So we need to find I. Let's see how to find I. Now how will you find I? How will you find I of a system? We know that, let's say some body like this. So I am assuming this to be a ship. Now what? So this is looking from above. So this is the whole, this is the transverse section, and this is the longitudinal section. So what is this? We have like this. We are given like this. We are right. We are given like this. What did we call these things? Half. We call them half ordinates. You have to know this word because nothing else will be given. It will be just mentioned. The half ordinates of the ship are these values. I will be just given as a table. You have to know what that means. So half ordinates, it means these these distances. Okay. Of course, the ship won't be a box bar. Means if it's a box bar, there is no point giving half ordinates. You just need this one distance. Why? The ship will be like this. It'll be totally different. Means it'll be like this. So it'll be totally half ordinates will at different stations you need to do the for a complete ship. This is a real ship. So so these are the half ordinates. Now how do we find what I are we talking about? I for a rectangle in general is given by this half ordinate cube into L divided by 12, right? If this is y, let's call this y. I mean this y, sorry, this is y by 2, y by 2. So if this is y, then y cube into L by 12 will give you the it gives you the I, the moment of inertia. So how do we find the moment of inertia of such a irregular shape? It's like this. You do integral y cube dl divided by 12. Okay, integral y cube dl by 12 will give you the the I for this shape. Just 1 minute, let me check this, what they have done. Okay. We have to make another table. See, so what do you need? You need y cubed. Okay, you need y. It's not simple as such. It's tedious. So you need to get y cube. What is y cube? It's half ordinate cube. Means these half ordinates cube you have to do at each station. You have to put a and then you have to find the total, means summation. So what exactly do you have to sum here? You have to sum to get this I. You have to sum the half ordinate cubed to get your this is what you are summing. So this half ordinate cube you have to sum over the whole length of the ship. That will give you your I. Means I am explaining from the basics so that you know what is this I and how it is coming here. Note that I'll just repeat if you want. I, what we want, the moment of inertia, is actually the I of this. Means if the ship is like this, this is of course the top view of the ship, this is the center line, and this is one half ordinate. Okay, the ship is like this. So half ordinates are like, these are different stations looking from above. These are different stations. I think they have called this to be station 8, and this is the aft of the ship, this is station 0, and here it is station 8. So the ship is divided into different stations, and you have at each station you are given the half ordinate. Now your real moment of inertia comes as, I am not exactly sure if there is a 12 in the derivation. I think it's just for a rectangle that 12 comes. I have to check that. I think the the general expression is y cube dl. Okay, the general expression for I is I cube dl probably. Is that correct? I don't know if you remember, but I'll check that and tell you. So at any rate, it becomes y cube. You need to get y cube dl. So you need to find this summation. Okay, so this half. So you are actually going to sum this half ordinate cubed over this entire section of the ship. If that is clear, then you will be able to do later also if you want to find I later, because the shape is not going to be similar, and but that concept is clear, means you will be able to extend it to different kinds of problems. So the idea is I is always comes as y cube dl. Okay, in general it comes as integral of y cube dl, not y cube dl, integral of y cube dl, where y is this distance. If this is the center line, y is y at each of these points, and dl is this distance. So it's like this. This is your y, this is your x. So integral y dx. Y, is it clear? If it's not clear, then okay. This is, so the table probably should help you. Actually, I am seeing a lot of confusion. I think I'll explain this probably further once more. That is, I'll do one thing before I know this probably. That is, suppose I'll do something just to make this simpler. That is, suppose you have a rectangular strip. Suppose you have a rectangular strip, and suppose that you are told that this is b by 2, this is b by 2, and let's say that the total length is L. Now suppose you have to find the moment of inertia of this body, of this area about this axis that I have drawn here. Okay, let's do this very simple thing. Now note that the moment of inertia is also called the second moment of area. You will see it's the same thing. Okay, I'll write it in both the ways. Let's call this axis. Okay, about that axis is given by let us do one thing. Let us consider, our idea is to find the moment of inertia of this whole strip about this axis. Let us take a small region of length dB. Okay, first we find the moment of inertia of this small region about this axis. It is given by, let's call this, let's say it's di is equal to this moment of inertia L into b square dB. This is the definition of this is the basic definition of moment of inertia. Okay, so you get di, then from this you can, what you are seeing is, from this it's basically coming like this, b cubed into L divided by, okay, that is how you are we'll see that. That is, now this is that I of this one small region. If you want to find the total I of this entire body, it will be I, it will be given by, let's call this 0. So okay, I'll continue here. Okay, b by 2. Now this becomes LB cube by 12. This is just to, this derivation was given just so that you get some idea of what is moment of inertia. This is the general idea, this is the basic definition of I. So from this di, this is how you proceed to get a moment of inertia of some surface. Now for this problem, if we come back, so we have, just like that rectangular strip we had, in this case we have some other body, and likewise we have these half ordinates. Now just like your LB cube by 12, you can, what are you doing here? You are actually applying that LB cube by 12 for small strips, and then you are summing it up using a Simpsons multiplier, and you are getting for the whole, you are getting the I for the whole strip. So for once, so how do you find? So you see that we need that half ordinate cubed, okay, to get the b cube. For that we need like L into b cube. So we are, for the one strip you need that b cube, that is half ordinate cube. Okay, then you multiply it by 2 so that you get for the whole. So half ordinate cube, then so this, let's see what this becomes. So this is 0, and half ordinate cube will become 0. So that means station 0 is taken as, station 0 I think is the halfmost they have taken this time. So station 0 has half ordinate, here the half ordinate is 0. So 0 0, Simpsons multiplier, okay, that we'll wait, then 0, this becomes, this is actually 12, half ordinate is 12. So for half ordinate cubed and 3, 14.5, 3048. Okay, I'll write 3 of these, and you will have Simpsons multiplier 1 4 2 4 2 4, like that. Okay, Simpsons multiplier. Then using this half ordinate cube, using this, you multiply this half ordinate cube with the Simpsons multiplier, I hope it's clear to you what we are doing. Is it becoming too complicated? No, that is, you have got the half ordinate cube, you multiply it with the Simpsons multiplier, you get a function of the second moment. You get here, you are actually getting your function of I, and from the function of I, you sum them up, sigma function of I, and to get your total I, final I, you will get, it will be again h by 3 into, okay, sigma function of I, h by 3 into sigma function of I will give you, now this, that is this thing. When you do this, you are actually getting the I of the whole body. So this I you need. Now in addition to this, they have also said that, remember we have started from station 0, this set of table that is given say goes till station 8. It has solved till station 8, and they are saying that forward of station 8 there is an appendage area which has a second moment of area of 30 meter power 4 in addition. Means beyond this station 8 there is some area which has an I equal to 30. Note that it's very easy to add the moment of inertias. You just add them. There is nothing to do here. There is no moment or anything. You just, so to get the total I of the ship, not I of the ship, let's call it the I of the water plane. I of the water plane is therefore equal to whatever I you are getting from this, whatever I you have got here, this final I, this summation plus 30. So I plus 30. This gives you the total water plane of the ship. This is your I. Okay. This more or less ends the problem. Now it's very simple. What are you supposed to find? You are supposed to find Bm, which, note that we have already calculated del, which is the volume, total volume, underwater volume of the ship, and here we have calculated I. Therefore you have to have I by del. You just apply that, you will get the value, and then I think we have already calculated Kb as well. Then their question was to find Km, I think. Yes, the problem of the question is Km. So you just add them together and you get Km. Okay. So this is the problem as such is not complicated, but there are a lot of things in it, and it can get, that's why I said if you are trying to do this for the exam, it will take probably 45 minutes. Surely it will take, because note that you are using the calculator for each of these stations. You have to multiply the half ordinate cube, then you have to multiply it with the Simpsons multiplier, then you have to sum them. It's a long process. So I won't ask such a big problem, but maybe half of this, so like this. All right. Then so I guess one thing that we saw that is how to calculate I for a body if you are given some half ordinates. That method, try to understand properly, but definitely be able to do it for the exam. So that is, you have to find the half ordinate, you have to find its cube, you have to sum that cube over the whole length of the ship, and that will give you the I. In case you have some other left I, you just add the I to it. I can be added just like that. Similarly, you might have a volume. Kb I have already defined many times, described many times how to find the Kb of a ship. So that is, these are the different things. And in case I give a problem which has these half ordinates, I'll explain to you how exactly to get the Simpsons multiplier. Okay, or that part of that problem will have a region where you have to derive the Simpsons multiplier. That's what I explained to you how to derive it. You know how to derive it now. I'll derive one case if you want. We'll see that. One more problem we'll do. One simple problem is that this is not that complicated. That is, you are told that there is a vessel with a displacement of some value 22,600 tons, and so just to repeat, these problems are simple. I mean, these are just applications, what I am going to do, but what I have done just now, that long making of the tables and all that, go through that as many times until that thing is very clear how they have done that, because that is the main problem. It's not just for this course, of course. I mean, when you're doing it, that's what you'll be doing in shipyards and all. If you take up a job in shipyard later, you will be trying to find these kinds of KBs or BMs, GMs, like that. Okay, so that is very important. Now here you are told that the displacement of a vessel is 22,600 tons. You are told that kg is equal to 8.2 meter. Then you are told that it discharges 3,000 tons of cargo of ballast. Does anyone know what is ballast? Have you heard that word? Okay. Ballast means water that is taken into the vessel for many purposes. You take that vessel in, you leave that water out. Means usually taken from the sea itself. From the port, they take water. The main reason for this ballast is to, suppose you want to increase the draft, means you want to push the ship down, you take in water, then obviously it will come down. Okay, and similarly when you want to push the ship up, you remove the water. So that concept of going up and down, because by taking in and relieving water, that process is called ballasting. Okay, and do I have time to finish this? Okay, so I'll just explain this. So that is ballast. So you will take in water and leave it, and that water is called also ballast. So ballast water. So it says that it discharges 3,000 tons of ballast, and it is really that kg of that ballast is 2 meter. Means this is just to find the net kg. You are told that kg of the ship is something, then you are told that some ballast, that is water, is removed at a kg of 2 meter, means that is that water itself is a body, is a weight with a kg, means its center of gravity is at that kg, it's at that value, and therefore using the 2 kgs you can find the final net kg. That it's just to do that. So, and similarly, just to make the problem, that is, it says that then she loads 11,800 tons, that is the ship then loads 11,800 tons of cargo at a kg of 7.8 meter. That is their new kg, not the new kg. Note that these are the different kgs of different weights: kg of the ship, kg of that ballast, kg of that cargo that is added. Okay. Now you are told that you need to add a further of 1,200 tons somewhere. With kg of something, you have to add. Now this is what you have to find, and you are told that GM has to be at least 0.5 meter. Now what else is required? Okay, you are also told that Km at 32. Okay, I will do this, and then actually there is no time. We will continue this problem in the next class. Okay, this is a very simple problem, but as I said before, do the other problem carefully. The big problem is making that table and getting it correct. It's a big problem. Okay, thank you.